So let's start talking about intermediate operations in more detail. You've already seen kind of what they do. They sit between the source and the terminal operation and can do they can have various behaviors that will have some type of impact, either transforming or reducing or whatever, filtering the various elements as they flow through a stream. And what's interesting about these operations is that they apply to both sequential and parallel streams. And one of the really cool things about Java 8 streams is the fact that once you know how to use sequential operations, you can pretty much program parallel streams with very little additional effort. And so I always like to say that being a good streams programmer will make you a better parallel streams programmer. So I'm going to show you how the intermediate operations work in the context of the simple stream program. And keep in mind a couple things. First, intermediate operations are lazy, and they only run after the terminal operation is reached. So let's start by talking about the map operation. That's a very common operation. So what the map operation is going to do is it's going to apply a mapper function to every element of the input stream, and it's going to return an output stream consisting of the results. And so as you can see here, if we have a stream of input where we're going to apply map, then a couple interesting things are going to happen. One thing to note about map is that the number of output stream elements must match the number of input stream elements. So there's always a one-to-one correspondence between input stream and output stream with map. Now, naturally, if the mapper function or the behavior throws an exception, then that could terminate the stream, which is sometimes necessary, but we don't always need to do that. So usually, 99.9 times out of 100, the map operation will run to completion. That's why it's a run to completion operation. Here's a simple example for our simple search stream program. We take the search words for a given input string, and we're going to map those search words using the search for word method, which will try to see where, if anywhere, in that input string a given search word appears. So search for word is going to be applied to every element of the search words input stream. And map may transform the type of elements it processes. And in fact, in this case, it does. So as you can see, map takes in a stream of strings, which are the words to search for, and it turns them into a stream of search results, which are the output elements in this case. So you can see a transformation occurred. You don't have to transform. Obviously, you could do a string-to-string transformation. For example, you might go from uppercase to lowercase or something like that. But you can do transformations. And then this is the way we do it. We have the map operation as a fluid, cascading set of method calls. So that's map. So what we're going to talk about here is the mapToInt intermediate operation. And we've talked before about map. As you may recall, map is something that takes a stream of reference types and converts it to an output stream of reference types. So that's what map does. mapToInt is a variation of map that will return something known as an IntStream that consists of the results of applying the mapper function to all the elements of the input stream. And so that sort of raises the question, what is an IntStream? So an IntStream is a specialization of stream that's designed to work on int primitives. So again, you probably recall in Java, we have these kind of dual type systems. We have all the reference types, which are things that are based on classes. And then we have the primitive types. And primitive types are things like int and long and double and so on. And so those are two distinct type systems for a variety of odd reasons that go back to the history of Java and how it was designed. And so an int stream is a specialization of stream that works on ints. And so mapToInt is designed to take something that comes in as a reference type, as a stream of reference types, and then convert it into something that is a stream of ints, or an int stream. Just as with mapToInt will take X number of elements in the input stream and do the transformations, and then it'll create an output stream with the same number of elements that were in the input stream. So they're equal. Unless, of course, an exception is thrown, but we're not going to think about that for the moment. So the example program that we're going to be talking about a little bit later when I talk about something called the compute max method is going to take a list of indices which are going to come into this particular intermediate operation as a stream of indices, and it's going to transform the stream of indices, they're called results, into a stream of primitive int indices. And you'll understand a little bit later about why it does that. What it's going to do is it's going to create this stream, and then it's going to go ahead and pick the maximum element. We'll talk about that in just a bit. So as with mapToInt may also transform the type of elements it processes. In this particular case, it transforms a stream of result objects into a stream of ints. So that's the transformation that takes place in this particular case. So it goes from a reference type to a primitive type. And this is the way in which we use this particular method. I'll go through this example in more detail shortly. This is just the Cliff Notes version. But as you can see, there's a method called compute max that takes a list of result objects, which of course are reference types, and it creates a stream of these result objects, and then it maps that to int, and then computes the max of this. And as always, we have the cool fluent style programming where we cascade the methods together. But the key point here is we're transforming reference types to primitives. And why this is relevant is you should probably try, just for kicks, in your assignment 2 solutions to use mapToInt along with the sum terminal operation rather than using map with the reduce operation. Map with reduce works just fine, but I think it's a little bit cleaner to have mapToInt and then sum it. Just looks a little bit cleaner to my eyes. So that's why I wanted to introduce this particular topic. So that just kind of gives you an overview of mapToInt, so you'll understand a little bit better what it does. So it's a transformation method that's guaranteed to change something from reference types into int types. And of course, it may do other things as well as a result of the transformation. The next thing we have is the filter intermediate operation. Filter tests a predicate against each element of an input stream and returns an output stream containing only the elements that match the predicate. So this is a little bit different from map, and it's different in a couple different ways, as we're going to see here. Probably the most important difference between map and filter is that the number of elements in the output stream for filter could be less than the number of input elements if it doesn't pass the filter, obviously. So if you do have everything matched, then of course you'll get back the same number, but that's not always the case, and in fact that's the point of filter. You can think of filter as kind of being like an if statement, if you will. Think about filter. Whenever you're tempted to have a loop that's looping through a collection and you want to be able to access and do something conditionally, remove the urge or resist the urge to use an if statement and use filter instead. That's kind of what its purpose is. So we use filter in order to be able to get rid of empty search results. So if we have something that didn't happen to match for whatever reason, we would end up with a stream that had fewer elements. Now, obviously, if we search for the words do, re, mi in the do, re, mi song, we're going to find them, but that isn't always the case. Another thing to remember about the filter operation is it can't change the type of the elements that it's processing. Map can change it, but you always get back the same number of elements. In contrast, filter will return fewer elements, potentially, and it can't change the type. So it always has to have the same output type. Here's how we do that. Yes, sir, Gavin. No, that's actually a really good question. Filter only has the ability to not let something through. So it's actually, I'm trying to think of a good example of a filter. Like if you think about a water filter, it actually does change what flows through it, conceivably, if there's impurities in the water that it can detect. This is a slightly different kind of filter. It's filtering stuff out. So It's more like a filter that might filter, I'll have to think of something, but think of an analogy where the things that go through or remain unchanged. But that's an excellent question. Yes? Great example, yeah. So from the real world or the virtual world of computing, then what filter's doing is it's just saying if something doesn't match this condition, don't let it through. If it does match the condition, let it through. I'm trying to think of something in everyday life where you filter something and it doesn't have any effect on it. Maybe it's like if you go to a really swanky nightclub and they only let like certain types of people in, right? If you're dressed in a certain way, they don't change the people who they let in, but you're filtering it. I'm not sure if that's a good example either, but you get the point. So filter can't make changes, but it can return fewer things, whereas map returns exactly the same number, but can make the changes. The third type of intermediate operation we're going to talk about is a little bit more interesting in some ways because it's a stateful operation. Map and filter are not stateful operations. And so what they do is they don't, they will look at every element that comes past. dropWhile, and there's another one called takeWhile, are stateful intermediate operations. There's two sort of variants of dropWhile. The method looks the same, but the main difference is that it depends on what characteristics there are of the stream of data that's coming to it. So let's assume, for sake of argument, we have a so-called unordered stream. So an unordered stream, as we see here, is simply going to be some input in just whatever order. It's not sorted. So if the stream is unordered, then dropWhile will return a stream consisting of the remaining elements of the stream after we drop a subset of the elements that match the given predicate. And we'll talk through this example in a second to see why you might need this, but that's basically what it's going to do. It's going to drop everything that doesn't equal the condition, and then when something matches the condition, it returns the remaining elements in the stream at that point. Then there's also something, so the other characteristic is, what if the stream is ordered? So if the stream is ordered, then it's going to return a stream consisting of the remaining elements of this stream after dropping the longest prefix of elements that match the given predicate. So that is a subtle point. The reason why this is important, this distinction, is if you use dropWhile for an ordered parallel stream, then it's going to be very expensive because all those different threads are going to have to figure out what's the longest prefix, the longest contiguous section of matching elements in counter order. And that gets tricky. And so that's a good example, actually, where you don't have embarrassingly parallel behavior. And so the streams framework will, in fact, give you the semantics that you're asking it to, but it's very inefficient internally because it has to coordinate between all these threads that would really like to run in an embarrassingly parallel manner. So that's one of the tricky parts with that. The number of output elements in a stream with dropWhile as an intermediate operation may be less than the number of elements of the input stream elements, which makes sense because we're dropping them, right? So if things are not matching the condition, we're going to be dropping them, so we'll end up with less elements. However, and this is a great quiz question, the semantics of dropWhile differ from the semantics of filter. And here's why. With filter, you have to look through every element in the input stream to decide whether or not it's going to match against the filter expression, in which case, if it does, you let it through. If it doesn't, you don't. With dropWhile, you don't have to look through everything, because as soon as you find the first element that matches, then at that point, you're basically done. So you don't have to look at everything. And as we talked about before, some operations can change things, some operations can't. dropWhile cannot change the type of elements it processes. It can only drop stuff up to some matching condition. And here's how we use this, and I think I walked through this in a bit more detail. Yes, okay. So I'm going to show you how to use dropWhile. The other examples we looked at for map and for filter, we already had talked earlier when we looked at the visualization of the program to kind of get a sense of what it did. This one is a little bit more complicated, so I'll show you how it works kind of in sequence, and we'll see what dropWhile is going to do. So this particular use of dropWhile is to print a slice. We're going to print a slice of the stream. And we're going to print a slice by we're giving it a word, and we're going to say, drop everything up to this word, and then print everything after this word, or including that word. So in the context of our do, re, mi program, if we have, do, re, mi, fa, sol, la, ti, do, and we say, I want to basically print a slice from, la to the end, then this little piece of program here we're about to look at will do that. It'll print all the indices for la and ti, but it'll skip all the other ones. So what we take as input to this program is a list of search results. So we have a list of search results, and we're then going to go ahead and collect those things together to have a hash map, or map, actually it's a linked hash map. I'll talk more about that in a second. We're going to have a map that will map the words as the keys in the map, and then the values will be where the words appeared, if they appeared anywhere. So that's what collect is going to do. It's grouping by is a collector, which I think we've briefly talked about, and it's used to classify things. So we're going to classify this by the keyword, do, re, mi, fa, whatever. It's going to classify it by that. And we use a linked hash map so that it'll keep track of the order in which the items were inserted, even though the hash map will, of course, put them into the hash map wherever they happen to go. And linked hash map is useful because when we iterate through it, it'll go in the order of insertion. So it'll be, do, re, mi, fa, sol, la, ti, blah, blah, that kind of thing. So once we create this hash map, we then take the entry set of the hash map. So remember, a hash map contains a map of entry set key value pairs, right? Key being do, re, mi, fa, whatever. The value being what indices those appear at. And we convert that entry set into a stream. So now we have a stream of entries. And because this was a linked hash map, then when we get the iterator for that and turn it into a stream, they come out as do, re, mi, fa, sol, la, ti, do, or whatever, even though the hash itself could put it in whatever order it wants to. So what we're going to do is now we get a stream of these key value pairs, these entry sets, coming through the dropWhile intermediate operation. And we're going to drop while the next element in the stream has a key value that doesn't match word. I don't show not equal, but you can just imagine it checks to see whether or not the next element's key matches word. And if they are equal, it returns false. If they're not equal, it returns true. So it's going to skip over everything that doesn't equal the word. And when it finally gets a match, at that point, dropWhile says, OK, I'm done. And it returns the remaining elements in the input stream that are going to be equal, at least the first place where it hits something that equals the word we're searching for, it'll return the rest of the elements in the stream. And then we take the rest of those elements in the stream, and for each of them, we go ahead and we print them out. So interesting. It would be kind of fun to write the code to do this without using Java 8 streams. I think you would discover that it was a lot more tedious. You'd have to write loops that would go through and take the entries in the list of search results and throw them into some kind of map or whatever you wanted to do. And then you'd have loops. It would be very complicated. You'd probably have nested loops, and it would be rather ugly. So the nice thing about this is once you know streams, you can just sort of read through it top to bottom, and it all works quite nicely. So that's the end of our discussions on intermediate streams.